This is going to be somewhat of a explanatory video. Again, I haven't been doing a lot of stuff on camera because it's just too time consuming, and I'm impatient. So what happens is that I want to fix something and I have to concentrate on this stuff, and I only have a handheld phone, so it's difficult to actually do the repair or diagnose any kind of problem while on camera while I'm doing it. Maybe later on I'll get a tripod or try to do something. Anyway, this is an interesting video though. My last set of videos was again on the Tds540 scope, and I had placed these heat sinks, and you'll notice one is missing from the MUX chip. I'll try to hope this thing focuses. Anyway, and I'll explain why. I had placed these three, actually there were four heat sinks on the top of the MUX chips in my last video, and installed the board. And I think the last thing I said about this scope was that it's the bane of my existence, and it really is. I was using it, and basically what happened was I tried to run a signal path compensation, and it failed. And then I tried to run a diagnostic, and it failed. It failed with a diagnostic glitch trigger error and a DAC range failure. So I took the board out. This is the actual board from the unit itself. Let's do a quick scan here. All of these chips are replaced. See, this is what makes it difficult. This digitalizer I replaced. This is the old one. Now, I didn't do this time, but this is over the lifetime of fixing this thing. And this MUX chip, which is right there. All of these were gotten from this donor board that I have here. And I don't have a microscope, so I had to do this all by, I guess you could say, remote control, so to speak. And what I mean by remote control is just do it the best I can with the magnifying glass. It was very tedious, to say the least. But anyway, the point is, very quickly, or I'm not going to say very quickly, but maybe this will help someone that's working on these. I know that it would have helped me a lot if I had a video like this. And that's what the purpose of this is really just to kind of explain what is going on here. Anyway, sorry about that camera angle there. I had to pick up the board. I had looked around, and this board is so destroyed because, as you can tell, all of the caps have been changed. And it is in particular, it's always been in particularly bad shape, because if you look at this donor board, for example, it's in a lot better shape, but it never did work. This is from a, you can see, a 544A, which is the same architecture exactly, but it has the old electrolytic caps, which basically spill electrolytic all over everything. And this is a donor board I have that I just basically scavenge things off of to use. But anyway, the point is that when I got this scope here, this board was in tremendously bad shape. And it's very difficult to work on because the electrolytic was just all over, and I think it was ran for an extended period of time with the electrolytic all over the board, and that caused a lot of problems. Makes it exceedingly difficult to solder to. In fact, I have to use this Amtech, which is, this stuff is great. It's absolutely great stuff. To even begin to get a good solder joint. And the board looks fairly clean here. I don't have a ultrasonic cleaner, and that's really what it needs. So I basically just use alcohol and some simple green and scrub this thing many times. But anyway, the point is that whenever anything breaks, the solder, the pads tend to lift. And I noticed that there was some lifted pads on the old MUX chip. And the error that I was getting indicated that there was a DAC range failure. And I really did jump the gun on this, and it is my fault. I should have tested it further before I jumped the gun. But I noticed that there were quite a few pads that were loose. And I guess I just got aggravated, and I decided that I was going to repair what pads I could repair, and the other ones I would jump. And that's why there's this, I don't know how well you all can see it, but there's this Frankenstein monstration of jumper wires going on here, because that's how I basically have had to fix this board. Anyway, the point is that I removed the old mux chip by cutting it out, which is kind of terrible because these things are irreplaceable. I repaired what pads I could using some high temperature adhesive, and if you all are interested in that, just let me know and I'll give you the name. I think it's from Chemtronics, if I'm not mistaken, makes it. Same people who make this stuff here. Anyway, that's, of course, that's not the stuff. That's tuner cleaner. That's contact cleaner. But anyway, and the ones I couldn't repair, I used jumper wire on. I managed to get this mux chip off of here, believe it or not. Sorry, here. And I did not use Chip Quick, which is what I used to replace the dig. In fact, you can tell on the leads. I used Chip Quick to get this off. I didn't. I basically just used a hot air gun. And I really, at that point, didn't think this thing would ever work again. I took my time, and I got it off fairly intact, to be honest with you. I managed to flow, using drag solder techniques and spot solder techniques, the mux chip back on, and hooked it all up. And to make a long story short, turned it on, and it booted up properly. No errors in the diagnostic, and it ran signal path compensation correctly. Anyway, I thought I had it licked, and a little while went by. I tried to do it again, and I got the same error. So obviously, it was an intermittent fault. This, was not the problem. Although the pads were beginning to lift, and there was a problem with compromised pads that probably would have led in the future to additional problems. So anyway, what I eventually tracked it down to was, let's see, I really can't see exactly, this is the problem, was to this guy right here, 905, U905. And what the problem was this is a demux chip, or a selector chip, I should say, which is used to switch in an analog multiplexer between the DAC and the charge pump or sample and hold circuitry, and is used to feed back the DAC voltages as well as signal path compensation voltages so that they can be sensed through the digitalizers. With this thing bad, it basically made that entire circuit inoperable. So I managed to trace this using my other Tektronix scope. I got it off the donor board, placed it on here, and it started working consistently. Except now there was another problem. And this is the problem that maybe might help some people as well. I was getting a sawtooth wave on two of the on two of the channels of about a maximum of 2 volts peak to peak. And I could not figure out where it was coming from. I thought maybe I might have screwed up the whole digitalizer problem, by putting this new mux chip, because that is a lot of pins to solder without a microscope. But that was not it. I basically tracked down that there was a signal being injected onto the preamps, and that signal was being injected onto the offset, which is used to offset the trace via the DAC circuitry. So we were back to the DAC circuitry again. Anyway, I tracked it down to this guy here, 943, And that is an op amp which is used to offset the preamps. Anyway, the point is that I looked on the input to those op amps, and it was on the input of those op amps. It was not the op amp itself. Now, one of two things was happening. Either there was something wrong with the op amps, that there was a low impedance situation, because the DAC is based on a charge pump or a sample and hold, whatever way you want to term it, circuit design. And after it basically refreshes the charge starts to decay. So you need a very high resistance level for it to be maintained, or it will decay and it'll create that sine wave, which will create instability, will be magnified throughout this entire circuitry, and will make it impossible for signal path compensation to complete correctly. So anyway, I traced it to the input of those op amps. The op amps looked fine. And to make a long story short, I eventually came to the conclusion that it was gunk that was around in this circuitry area from the solder paste, not solder paste, but from the flux, and the use of not 100% or 99% alcohol. I think that the solder paste Amtech claims that it's non-conductive, which I think that it is non-conductive. I don't think they're lying. But I think what happened was the 9% of water in this alcohol mixture here was absorbed into the paste itself. And basically it didn't dry that quickly. It insulated it from evaporation. So I decided to wash the board. I washed it in hot water with soap. And you could just smell the flux coming off of it. Let it dry out. Put it all back together again. And it worked. The sawtooth wave was gone. The only problem now is that I was getting an error with this guy. Due to my poor soldering, which actually was pretty good soldering, if you can kind of tell. I don't know. This is not really ideal in terms of... Let's see if I can get more light. All right, well, anyway. The point is, as I said, I don't have a microscope. So what I had to do is I had to use a fine pin tip for my soldering iron and touch up each one of those pins individually. When I did that, I got it to come back to life, and now it seems to be working just fine. So the next step, of course, is to put it all back together, clean it up. My fast Fourier transform option, which is the advanced math option, 1M, and 2F is the advanced math option, and 1M is the deep memory option, were reset because of the problems I'm having. So I'm going to have to use my GPIP project to re-enable those. And I don't know how long it's going to go again before something else fails on this thing. It seems to be entering its, it's at the end of its useful life. I don't know. But anyway, this is kind of what it is. So anyone who's working on these, make sure the analog section, the digital sections obviously are not that prone to contamination, but the analog sections have to be very, very clean. This thing is very, very sensitive, and any type of parasitic conduction, any type of substance which might change the impedance on this board, whether it be moisture, whether it be electrolytic, whatever, dirt, will be amplified through these circuits to such a degree that it will not pass signal path compensation, and you'll have all kinds of problems. So anyway, the point is I'm thinking about getting a microscope and touching all this up before I put it back together. It does work. I have had it back together, but I took it apart just to clean the board again. And so if anyone gets a 6 millisecond sawtooth looking wave, It's from that parasitic conduction, which is going into, which has to do with the DAC section, which that's this section right here. In fact, the DAC is right here, and these are all the analog switches and the selectors for the analog switches. And this here, this went bad originally too. I had to get this and actually, let me see, where is it? See right here? I had to actually cannibalize that off of this board because this was like at 1 mega ohm. It was basically open because of all of these capacitors leaking electrolytic onto here. So I had to replace this originally just to get this thing to work when I first bought it. So anyway, that's just kind of a quick, oh yes, and one other thing. The two lines you see right there, this is another way I screwed up. Two of those pads were pretty much, unless I wanted to cut out some, let me see if I can get that to focus. I don't know if it will or not. Unless I wanted to cut out some copper and then use the high temperature epoxy to make my own traces and my own pads, which I've done before and really is probably what I should have done here, but I didn't have everything I needed to do it. I didn't have the copper. I did have the epoxy, so I just figured I would jumper them and just get it done. Quick story that's kind of interesting here. Those lines are basically differential clock lines. Those clock buffer circuits clock the main digitalizers right here at 250 megahertz. They basically then create two channels of data, channel A and channel B, each 8 bits wide. They are clocked into the multiplexer chips at 125 megahertz each. Yes, I think that's it. I'm almost positive. Anyway, the point is that I didn't realize at the time. I realized it, but it just didn't occur to me. And I'll turn the board over, and I have to kind of show you this, so hopefully I won't drop this thing, and that's why I don't do these videos too often. Let me see if I can get this turned around. Okay. Now, let me see if I can find it now. Okay, you see? And if this thing will focus. And if I can actually spot it myself. Okay, where is it? Where is it? I could see it when I don't look in the camera. I really can't see it otherwise. Just bear with me, please. I think it's because of, okay. There it is. Now, let's see if this will focus. Those two right there on the left hand, extreme left, those are two resistors which are in series with the differential clock lines. I removed those and I made my own wires. Now notice the wires that come out there in that zigzag pattern. Look at the top. That runs from the MUX chip to the digitalizer, or I should say from the digitalizer to the MUX chip, because it's what's driving the MUX. Notice it's in a zigzag pattern. Now, why would it be like that? Why not just run it straight? And the reason is because that's a delay line. All of these 4 channels can be interleaved, so they basically have to be clocked at about the same time. And because of propagation delay, those traces are made as a delay line to compensate for that, so that all of these basically are clocking at the same time. But then when you use just one channel and you get up to the 1 gigasample a second sampling rate, what it basically does is some circuitry kicks in which delays slightly each one, so that each sample is slightly off skew or slightly off from the other in time, is related to time. It's an interleaving technique. And that I knew that's how it worked, but I just didn't think about it at the time. So that's a real problem, because it has to be sampling different from these others in order to get the 1 gig sampling rate. So I had really made a mess, is the point. So what I did to fix that without having to pull the chip off and et cetera, was I measured the length roughly of the trace itself. And then I made a strand of wire, which is that wire right there, you can tell. Those underneath that shrink wrap is where the resistors are. And I basically twisted them in a twisted pair so that they, don't interfere with each other, because they are differential pairs. And that wire is approximately my delay line. It's not perfect, but it really doesn't have to be perfect. And as I said, it passed signal path compensation and everything works. So this thing is becoming a real Frankenstein monster. One of these lines is for the D1 bus, which is in parallel of all of the MUX chips. And that pin was missing. That pad was missing. So I basically ran a line all the way here right to the interface itself, which you can tell. So I guess that kind of explains it all. This is like a 22-minute video. And I know there's not much excitement in it, but there's a lot of information here for someone who might be fixing this stuff. And if anybody has any questions or, wants to make any comments about how bad the video is or anything else, please let me know. This is the donor board again. And, you can tell I haven't cannibalized all of this. It came, the heat sinks were missing, and I've used that and I've used that. And I don't even know how good all this stuff is. You know what I mean? The board didn't work. All the chips were present when I got it, and I plugged it in, and I couldn't get it to do anything. So I've been trying to rescue this one, and as I said, it does work. I will be making another video when I put it all back together, although, as I said, I have had it together, and it does work. And I probably will be making a video just to show you all that it passes signal path compensation and diagnostics, and then me enabling the deep memory and the advanced math options, fast Fourier transform and integration and differentialization, the calculus functions. So anyway, that's it. And I hope you all enjoy it. And toodaloo. Bye.